Welcome to Graph Theory, Adiabatic Quantum Computing Methods by N.B. Singh. This book explores how quantum computing intersects with graph theory, offering insights into both theory and applications. We delve into quantum algorithms designed for graph problems and explore their potential in various fields, from cryptography to machine learning. This book aims to introduce readers to this exciting area and inspire future research and innovation. Introduction to Graph Theory. Graph theory is a fundamental area of mathematics that examines the relationships and connections between objects, represented as vertices connected by edges. This chapter introduces the core concepts and definitions of graph theory, which form the foundation for exploring its applications in various fields, including computer science, biology, and social networks. We will cover essential topics such as types of graphs, graph properties, and basic algorithms. Understanding these basics is crucial for delving into more complex topics like adiabatic quantum computing methods, where graph theory plays a pivotal role in modeling and solving computational problems efficiently. Through this chapter, readers will gain the necessary knowledge to appreciate the depth and utility of graph theory in both classical and quantum computing contexts. Definitions and basic concepts. In this section, we will explore the fundamental definitions and basic concepts of graph theory, which form the foundation for understanding more advanced topics in this field. Graph theory is a branch of mathematics that studies the properties and applications of graphs. A graph is a collection of points, called vertices, connected by lines called edges. A vertex, plural vertices, represents a point in the graph. For example, in a social network graph, each vertex could represent a person. An edge represents a connection between two vertices. Continuing with the social network example, an edge could represent a friendship or a connection between two people. Undirected graphs are graphs where the edges have no direction. This means that if there is an edge between vertex A and vertex B, you can travel from A to B and from B to A without any restriction. In contrast, directed graphs have edges with a direction, meaning that each edge has a starting vertex and an ending vertex. For instance, in a graph representing a set of tasks, an edge might indicate that one task must be completed before another can begin. Simple graphs are graphs that do not have multiple edges between the same pair of vertices and do not have loops, which are edges that connect a vertex to itself. Multigraphs can have multiple edges between the same pair of vertices. Pseudographs are graphs that may contain loops and multiple edges. Another important concept is the degree of a vertex, which is the number of edges connected to it. In a directed graph, we distinguish between in degree, the number of incoming edges to a vertex, and out degree, the number of outgoing edges from a vertex. A path in a graph is a sequence of vertices connected by edges. If you can start at one vertex and follow a sequence of edges to reach another vertex, you have found a path. A cycle is a path that starts and ends at the same vertex without repeating any edges or vertices, except for the starting-ending vertex. Connected graphs are graphs where there is a path between every pair of vertices. If a graph is not connected, it is called disconnected. In the context of directed graphs, a graph is strongly connected if there is a directed path from any vertex